Welcome back, everyone. Today we're going to look at integer handling in Nasm. And over here on the right hand side we have the C's version, where essentially we're going to write some prompts out, which is enter your number to the standard out. You press it out, then we're going to read from the standard in, that's the user's input. Then we're going to place the result into the buffer. Then after, we're just going to convert the buffer into an int. Okay, usually in C there are two ways of doing it. There's the first way, and later on we'll look at the second way using the function a2i, or as I call it, a2. Okay, so it's the same setup. We read it into a buffer, then we convert that buffer using this algorithm over here. Now this, so for example, say we input in the value, say 12. Okay, because when we enter it into the standard in or the read, we need to add, we press enter to move on to the next side. So that the new line is also included. So we have 1, 2, and a new line. And remember, this is all in string form. Okay. And so, of course, our count is 3 because there are 3 of them. And our index, when we're indexing through, we have 0, 1, 2. And also, we're going to have to convert that buffer into an int. That's how it works. So to be able to convert to an int, we follow a simple algorithm where we initialize our number or any variable you wish to 0. In this case, we're using number, and we're going to loop through our buffer. And if our buffer is equal to the new line character, then we exit. It's simply a double check, so we know from up here that my count is 3, so we're checking 3, and also when it's new line we exit. So it's going to do 0, 1, then it's going to exit, and also the same thing for this one. It's just going to do 0, 1, and it exits. It's just a double safety check for me. And also, so for example, if I is equal to 0, then we know that from our buffer is the first one, the index 0 is the first one. So we have 1, and remember the 1 is a character. So we're going to do 1 minus 0 to be able to get the actual value for, the difference is going to give us the actual value. What I mean is 1 in ASCII character is, let's have a look here. ASCII table, 1 is 49 and 0 is 48. So we're just doing 49 minus 48, which gives us 1. And also, so that's for the first part. And then when I is equal to 1, we have 1 times 10 plus the difference between the 2 and 0. So once again, bringing up the ASCII character, the ASCII table, we know 2 minus 0, which is 50 minus 48 is 2. Okay, it gives us 2, and then 1 now is an int. So 1 times 10 is, 10 plus 2, which gives us 12. And so it doesn't matter the size, the length of the buffer, we can simply use the same algorithm. So that's essentially what we're going to look at today. So it's the same thing written over here. Okay. And then after, we're just going to double the number. And in doubling the number, typically we do times 2, but I prefer to use the shift left and 1 because essentially, when we use a shift left, we're going to write the power of 2, which is essentially 1. So we use a shift left 1. This same notation can be written as this, can also be written as this. And after, we exit gracefully. Okay, so we have the same setup over here. So we have the prompts. We already know the prompts, so we have our prompt, the prompts are initialized. So we have our prompts and the prompt length, as we see over here in the Nasm. So we have our prompt, and the prompt length. Always remember to add a null terminator. And then also, we go to our very next line, which is writing to the standard out. And writing to the standard out, we've already seen it. So we have this form where one goes into the RAX, one goes into the RDI, the prompt and the prompt length. And whenever you do forget what goes where, essentially we have to look at the write is 1, which is this one. The standard out file number is 1, which is this. And then the prompt, and then the prompt length, okay? Then we do a syscall. We're telling the kernel to write to the standard out. And after, we also see that we have our char buff, and our char buff is uninitialized, so essentially it goes into the BSS section over here. And also read int is also uninitialized, so we also do the same thing here. We use the quad word, which essentially is 8 bytes, and it's basically, whenever I use it for 64-bit ints. So we do we reserve the quad word, which is the Q. We reserve 1, which is the 8 bytes, yeah. And so when we read from our standard in, over here, we're doing the read syscall. So our read syscall, we have 0, 0, and the buff, and then the 20, where the 0 over here is the sysread. The 0 here is for the standard in file number. Then buff and our 20, the same thing, read standard in file number, buff, and 20. And then after reading that, we check our error. I've already done a video on that. And we check our error by using the test RAX, and we're checking the sign. So for example, if the sign is negative, then it means we've already had an error. Then also we also check if the value itself returned is 0. What I mean is this. So for example, say our return value is -12, and -12 is represented this way using -12 is represented this way using the 2's complement. And so essentially, when the main, or when the MSB, most significant bit here, when the MSB is 1, it means it's negative. Okay, so essentially it does a test -12 against -12 and -12, a bitwise AND, and it checks. So we know that the MSB is negative. So for the jump, the JS, which is the jump if the sign, then we know that it's negative. So essentially what it does is it jumps to exit failure. And then it also checks the next flag, which is the JS, jump if 0. So in our computation, realize that it's not 0, because if it's 0, the 0 flag will be set. I mean, what I mean by 0 is the whole thing will be set to 0, and then it exits gracefully. So after this, we essentially place in the read system call, the value that we had for the read system call, into our new variable called the read int, and the read int is initialized here. And also, so we're done with this part. We're moving on to the next part, which is converting to an int. And for that, the int I equals 0, which is our index counter, I'm using the R8 register, okay? And also to num, I'm using the RCX register. So over here is the same as moving 0 into the RCX, which is we're just preparing it, okay? And so we enter into our loop, which is our first while loop, or essentially the convert to int. I'm terrible at naming, so please forgive me. We enter into our loop, and in our loop, we have our first condition, which is I less than the read int, and we know that the I is the R8, so we're checking the R8 against the read int, and if it's greater than or equal to, that's the invert of this symbol, which is the less than, then we jump to double the number, as I've already discussed. Otherwise, we move the byte into the byte of, this one, into the R9. Now remember, we see that there is a new operation over here, which is the move ZX. The main reason why I'm using the move ZX is because it actually stands for move with zero extended. Okay, and I'm using it because I'm trying to copy a smaller, like the byte over here, which is 1 byte, into a larger register, which is the R9. Okay, and when it does so, it safely fills in the upper bits of the register with zeros. What I mean is this. So for example, say we have maybe let's assume these are all 64 of them, and for the R9, let's say maybe this is R9, it contains maybe 64 zeros, and I'm saying, let's say we're moving some bits. Let's say, for example, we're moving maybe, I don't know, maybe 5 into it, so it looks like this now. Also, one might be tempted to use the lower bits, so we say R9B represents the lower parts of the R9 register. But the reason why I don't use the R9B, which is the lower parts of the register, is because, for example, what if maybe there's a value here, say 1, and when we continually use the R9 in our subsequent computation, it's going to assume the whole of this, which is not 5, but way greater than 5. Okay, this is 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 to the power 12 plus 5. Okay, and that's not what we want. So I tend to use the move ZX, where it writes the byte and it also makes the it writes the byte and also makes the upper parts of the register 0. Okay, so that's why I'm using the move ZX. And then after we compare it to the new line character, which is 10, a new line character. So essentially we're looking at this part of the condition. Then, so now we know that the R9 contains the buff I, so we subtract 48. What is 48? 48 is the character for, the ASCII character for, ASCII number for 0. 0 as in, over here, once again we look at it, so it's 48. Then, so we do a subtraction, so we do subtract R9 from 48. Remember that R9 now contains, over here contains the buff I, and then we're doing subtract 48, so essentially it's this whole part. Okay, and then after, remember we're using the RCX for our to num, so RCX, we're going to multiply the RCX value by 10, which is this part. Then after we're multiplying the RCX by 10. Then after we're going to add the R9, which is where R9 represents the whole of this. Okay, then the next part is to increase our counter, which is the R8. Then we loop again, then it goes back, and then it continues the same process over and over and over again. The idea is, why wouldn't one use, for this loop, why don't we use, say, directly the to num instead of the RCX? So the idea is this. I tried it over here. And our first while loop, instead of the RCX, I was using to num. And it turns out that you cannot have an instruction where both operand refers to memory and many like other instructions have strict rules on what combinations of registers and memory and immediate values they accept. Okay, so for example, this is not valid. Okay, and I think this is also not valid, and doing this is also not valid. We may have to specify the type of the variable and all that, but usually when I'm doing the math, I prefer to use a register, and then after doing everything, then I accumulate everything into a register. Then after I pass it back into the variable in itself. Okay, so for example, as we're seeing, I'm using the RCX, and after I pack the value of the RCX into the tunum. So once our loop is done, then I'm just saying that over here we're doubling, and the doubling, we see that we're using the shift left. It's pointing left, so we're using the shift left, which is essentially the same as multiplication by 2. Okay, so I'm using the shift left and 1 because the power of 2 is 1. And then after, I'm just passing the variable or the value into tunum, and this works fine. And then after, we exit successfully with an error code of 0. Otherwise, we write to the time where these fail. We write to the standard error, where the standard error value is 2, and then we exit with an error code of 1. Okay, so let's save this, and then let's try to compile or assemble it here. So when we try to run it, we see enter the number. When we enter 5, it's supposed to give us, say, we're doubling 5, so it's supposed to give us 10. Okay, but here's the case that we aren't printing it back to the screen, so we shouldn't see the 10, but we should just return back to our terminal. And then you see we return back to our terminal. So how then do we see that all that we did was right? Okay, so we're going to use a software called the GDB. Okay, and then we pass in the name. But to be able to use the GDB, okay, when you're linking, already in my run script, let's take a look at my run script. When you're linking it, we're going to have to pass in, using the Nasm, we're going to have to pass in the G flag, okay? And the G flags enables, debugging, so that GDB is able to make it simpler for us and see what's going on inside. So this is essentially my run script, yeah. And so we use a GDB, then our GDB opens up. I'm going to write our Nasm. I'm going to show us our Nasm code using the command code layout ASM. Okay. When we use layout ASM, we see that our notation over here is quite different. That's because assembly has two main types of assembly notations. We have the Intel, that's what we usually use, and we have the AT&T. The AT&T is mainly characterized by the percent signs. Okay, so we can convert this back to our normal Intel syntax using the following. Set this assembly flavor Intel. I don't get why we're not using the British spelling, which is like, U over here, but sure. And when we do that, let me lay out ASM again. Then we see that, it's changed, and that we have it in our syntax. So we're moving 1 into the EAX and all that, yeah. Okay, so over here I'm going to set a breakpoint because I want us to look at the value for, let me do this, micro integer handling, so we see our original code. I want us to read the value of tunum, and the tunum is actually set before the exit success. So essentially I'm setting a breakpoint to exit success at this point. So we write exit success. If you want to set a breakpoint to maybe using any of these as the reference, we do say star, then we do the 0x40, whatever value you want to use. Okay, so I'm setting the breakpoint to the exit success. Okay, so it should, after that you would see something like a B or something over here, B plus. So that's our breakpoint. So we try to run our program using the run command. I don't want debugging for this. It tells us enter your number. So when we pass in, say, 5, we're supposed to get 10, right? So at this point, it gets to the exit success. Okay, Now in the exit success, how then are we able to see the to num that we use, the variable that we used? It just so happens that we do the following syntax. Okay, so we have the format, then we have the size, then we have address. Okay, so our format over here, what happens is, so our format over here is D because we want the decimal format, and we're going to use G because the G represents the size of giant, which is 8 bits or like the 64, and our address is to num. Okay, so when we enter this, we should see 10 in the to num variable. So we see that yes, our code is actually working fine. Then of course, let me just do continue, and then we exit our program. We exit the GDB. And for instance, also, okay, maybe let me just run the whole process again and explain something. So we run the program. Let's say this time around, placing, okay, let's say still 5, and then we want to see the value in RCS because RCS also contains 10, because the 10 is going to be passed into the to num. Okay, so we just do info register RCX, or if you want, you can look at all the registers, but we see, let me just do the RCX instead because of the outputs. It's looking weird. Okay, so let me just look at the register for RCX. Then we see that RCX also contains 10. So this is how we are able to convert. Let me do exit. So this is how we are able to convert strings to int in Nasm. Okay, so I'm doing exit. Let me go this way. So there's the first way, and it is also easy to know that when we're doing, say, let me do int hand. Let me look at the C code. There is a second way. The second way is to use the atua function. Okay, and in the atua function we just do to num, and then we do atua, and let me see, buff. Okay, yeah, I think the atua is in the the standard IO. No, I think it's rather in the SDLib. Yeah, SDLib instead. Okay. And so how would the Nasm code also look like? So we see that I've taken out all of this convert to int. So in the Nasm code, let me just also take out all of this convert to int. No. Let me comment all of this out. And so how then do we use the atua? What we have to do first is, because it's a C function, we do extend atua so that we are able to use the C function to convert a string to int. Okay. And once we have this, how then are we able to do atua? So in Linux, to be able to pass in variables to functions, our very first variable, or the first argument, has to be in the RDI register. The next one goes into the RSI, the next one goes into the RDX, RCX, R8, and R9. Okay, so but atua only takes one argument, so we need to move the first argument into the RDI register. So we do move RDI, and let's say, for example, we're moving the whole of buff. How then do I even call this? So let me move buff. Okay. Then to be able to use the atwa, we just do call atwa, and our response or value is going to be in the array-x register, just like any system call. Okay, so I haven't tried this yet, so hopefully this works. And let me see something. Okay, because over here I'm using the RCX, so let me just use the RCX temporarily for, yeah, okay. So hopefully this works. So we compile using run.sh. Okay, no problems. String handling, we pass in 5. Okay, now let's go check our GDB again. And let's lay out let's set the disassembly flavor Intel. We're using the Intel once more. And let's lay out our ASM. And let's set our breakpoint once again to exit success. And then let's run our code. Okay, so I pass in 5. And then let's look at the value in the RCX register, and it also contains 10. So this is essentially what I wanted to show you guys today, that we are able to do two ways there are two ways of converting to an int. It's either we use the atwa function, or we can use our algorithm, which is the loop. And always remember to add the extend atwa, which is a C function to convert string to int. Okay, so usually I like to write those up here, and then we do the call over here. So this one I wanted to show you guys today, and thank you for watching.